Hey guys, welcome back. We got Gibbs free energy in this video. All right, and so what are we talking about like this? Well, we've learned some things. Let's go back to reactants and products. So we have reactants that react. And they're going to go to products. Now, we already know that enthalpy is here. And so this will have, the reactants will have some enthalpy. Right? And that's our heat content. All right? And then the products will have some enthalpy too. And depends on how much, like we could have a lot, we could have a little, right? And delta H then becomes from, right? We got delta H of the reaction, all right? And that's, if we remember this, this becomes delta H of the reaction. This is equal to the energy of bonds broken minus energy of bonds formed, right? Or, well, I won't go right there. I'm going to write delta H of the reaction right? Products minus reactants. Okay? Now, remember the goal, our thermodynamics goal, a goal, right, is to do heat into work. Right? We want to do heat into work, and that's a horrible work. Let's try that again. Okay? Right? And so for heat to work, typically delta H is negative. All right? It's exothermic. All right? And spontaneous. But it's not always. It's not always that way. A lot of times it is, but not always. It can be. All right. The other thing we learned, right? No, before we do that, a lot of times this is the chemical potential energy we talk about. Right? So why we have gasoline in the tank, right? Because it has chemical potential energy. And we burn it, or we have propane in the tank, right? Whatever we have some type of chemical potential energy that we use. Now, the other thing we learned about was entropy. All right, and we have delta S. And for spontaneous, right, entropy, whoa. What is this? This is the rearrangement of atoms. and the dispersal of energy. All right. Typically, delta S is positive for spontaneous, but not always. Right? Not always is it that way. Okay? So those are our two things we've learned now for thermodynamics. We got delta H for a reaction and delta S. So we got the heat transfer at constant pressure, and then basically the rearrangement of atoms and the dispersal of energy. How does those meld together, right? And so if we take a real example, right? Hydrogen gas and oxygen gas. All right. To make water. All right. So we have H2 gas plus 1/2 O2 gas going to H2O liquid, right? Because we're at 25 degrees Celsius, and we're going to say that EA has been met. Right? We have a spark, a match, right? All right. So now delta H values for this, if you look up in the back of your textbook, delta H, F standard, right? 0, 0, and negative 286 kilojoules per mole. S, your entropies, you're actually going to get 130.7 joules per mole. Okay. You get half of 205.2 joules per mole K, or K mole, doesn't matter how you do it, and you get 70 joules per mole K. All right, so delta H, if we calculate delta H standard for the reaction, right, is going to equal the sum delta HF of the products minus the sum, oh, that's horrible, the sum delta HF reactants. So we got products minus reactants. And so our delta H products would be H2O, H2O liquid, and just one of them. Reactants, H2 and O2. All right. Well, this is pretty straightforward. Delta H of the reaction equals negative 286 kilojoules per mole minus 0, because 0 and 0. So it's just the H2O value, which is right there. Perfect. So that's delta H of the reaction. That is the heat created by the reaction. So if you have a mole of hydrogen and half a mole of oxygen, to make 1 mole of water, 286 kilojoules is released. All right, now we got, so that's the enthalpy, right? This is the enthalpy, heat content. Now we have the entropy. At least they're really nice and close sounding. So you have delta S of the reaction, all right, and it's going to equal products minus the sum of the entropies of the reactants. I don't know if I wrote that up here. I did not write that up here, right? That goes up here as well, right? Because I have that. I should have that here, where delta S standard of the reaction is equal to S products that should be in there. Sorry about that. Okay, delta S products H2O minus H2 plus 1/2 O2. So delta S H2O is 70. H2 is 130. And 1/2 of 205.2. So I get delta S to be negative 163. All right. Now, at 25 degrees Celsius, right, or 298 Kelvin, right, are negative 163 joules per mole Kelvin multiplied by 298 Kelvin would be negative 48,574 joules per mole, or negative 48.6 kilojoules per mole. That means energy, right here, it's negative, energy in this system is less dispersed. That means our system got more organized. Well, that's a problem, right, for spontaneity, right? Or is it? Because delta S of the system right is negative for delta S standard of the universe to be positive delta S of the surroundings must increase by 48.6 kilojoules per mole. Which was 163 joules per mole Kelvin at this temperature. Right? So it's at 298 Kelvin, it's 48.6 kilojoules per mole. So if I have 1 mole of hydrogen reacting with half a mole of water, the surroundings need to increase energy by 48.6. Right? This requires heat from the system. All right. So what can we take away from this now so far, what we have? So for 1 mole of this reaction, which is H2 plus 1/2 O2 going to H2O. All right? 1 mole, negative 286 kilojoules, right, of heat is created. Right? To round a little bit, 48.6 or 49, about 49 kilojoules of heat is required to create disorder in the surroundings. Which means 237 kilojoules of heat, right? That's how much heat remains as quote unquote free energy available to do work. And of course, it came up as Gibbs came up with this, Gibbs free energy. And so delta G standard equals delta H standard minus temperature times delta S. Now, these are all for the system or reaction. Same thing in our case. All right. So, delta G, right, must be negative for a spontaneous process. Spontaneous right, so if we go back up to our reaction, right, this reaction right here, is that a spontaneous reaction in the forward direction? That's a good question. What do you think? Well, if you look at a satellite photo of the world, of the Earth, I would guess you would see a lot more of this than anything else. So this is spontaneous in the forward direction, right? We're not worried about lightning hitting the oceans and it breaking up into hydrogen and oxygen. We're not worried about that, all right? In fact, you're worried about these two reacting a lot, right? If you have hydrogen and oxygen gas, you got to be worried about sparks and smokes and static electricity and all that stuff, all right? So delta G is negative here in this equation, in this situation. Now, that means it would probably be enthalpy driven, right? So when you talk about driving force, you can, to make delta G negative, right? You can have 1 delta H negative, which would mean that it's enthalpy driven. Or you can have 2 delta S be positive, which means it's entropy driven. Right? Or both. Both could do it. Okay? Now, for this to happen, right, we're going to learn that T times delta G, delta S of the universe is equal to negative delta G, or proportional to at least, depending on how we do it. All right, now, one thing I want to point out, delta G and delta G. Delta G standard is 25 degrees Celsius, 1 atmosphere, 1 molar, so to speak. Delta G is any other conditions. So if we drop down to 20 degrees Celsius, you're at delta G, not delta G standard. All right, so this is why some things happen not at standard, even though there's standard. All right, so recapping again, delta G has 3 signs, 3 options. It can be negative, positive, or 0. If it's negative, we're spontaneous. If it's positive, you're non-spontaneous. 0 means at equilibrium. All right. So that's one way to calculate delta G. This is the first way. The next way we're going to calculate delta G is with the standard free energies of formation. Standard free energy of formation. All right. The Gibbs energy change I don't think it has apostrophe. If it has an apostrophe, I apologize. The Gibbs energy change that occurs when 1 mole of the compound whatever we're making, right? 1 mole of the compound is synthesized or made from its constituent elements in their standard states. All right. Now, just like delta H, elements in their standard state, right, have delta GF equal to 0. All right. So now, all right, the delta G standard of a reaction is equal to the sum of the free energies of formation of the products minus the sum of the free energies of formation of the reactants. So it's products minus reactants again. So that's the second way we're going to calculate delta G, if you have the free energy of formation. So there's different ways to calculate it depending on what we're doing, what data you're given. Now, there is, before we go, this is important, there's a temperature which the spontaneity changes. All right. I think I spelled that wrong. All right. Delta G equals 0 is equilibrium. All right. And so if we get delta G equals delta H minus T delta S, right? If this is 0, so that means we'd have 0 equals delta H minus T delta S, which means I'd have T delta S equals delta H. So that means temperature equals delta H all over delta S. And these are all of the reaction, right? Okay. And so this is a temperature. It goes from either spontaneous to non-spontaneous or non-spontaneous to spontaneous. So it's either way, right? What do I mean by that? H2O solid to H2O liquid. This is 25 degrees Celsius at 1 atmosphere, right? So as long as we're at 1 atmosphere, we know that this process occurs 0 degrees is the equilibrium point. So anything above 0, it's going to be spontaneous. Anything below 0 is going to be non-spontaneous. And we say 0, it's 273 Kelvin, right? So that's that. So now, that's what we're going to stop. And we'll see you guys in the next one. Take care.